And we're back. Welcome back from the weekend and happy Thursday. Now that the election is over, we can get back to business. So before we continue with our discussion on main memory, a few administrative bits. The reading, we have added to that by the 12th of November. Please have pages 349 through 371 from the main text. Make sure you're keeping up with your reading. Make sure to get that reading done. So at the airing of this module, we will have at the end of this week 4 weeks remaining in the semester. It is coming upon us quite rapidly. Written exam number 2 will be the week of the 16th of November. More on that on Tuesday's class. Homework number 3 has been out. It is due on Thursday, today, the 5th of November. Last day of classes, also a Thursday, the 3rd of December. Reading day, which is also division day of presentations, extravaganza, Friday, the following day, on the 4th of December. Please make sure you participate. A lot of interesting projects that people have been working on. Our scheduled final exam period is Thursday, the 10th of December, between the block of time 10:30 in the morning to 12:30 in the afternoon. You will be doing your final project presentations during this time. The last day of finals, our final project is due, and that is 11th of December at 8 p.m. All right, so why don't we continue? When we last left off, we talked about this process of swapping, and we said there's a special place on disk, namely the backing store, that is used to store the in-memory form of a process. And this backing store, because it's on disk, it's much more abundant in the amount of storage, and it's used to store your processes if all of the processes you're trying to run will not fit in main memory. But the trade-off is you get a tremendous slowdown order of magnitude when you swap things out because you're traversing the bus as well as writing to the disk. So let's continue on with allocation of main memory. And so the main memory, not only does it hold your processes, your programs in their executable state, it also holds the operating system itself, because the operating system is a program. It is a limited resource, your main memory, so you have to be very careful in how you allocate it. You have to make very good decisions, efficiency in your allocation. And so in the early days of operating systems development, a contiguous allocation of all of memory needed for a process was one of the ways that was used, but it was found that this wasn't the best way to do it. And so what they decided to do then was to chop up main memory into pieces called partitions. And now you had some parts of memory used to hold your operating system, which remained in memory, resident in memory, and the other parts of your memory were used to hold your processes. And so those privileged parts of memory had your operating system and the interrupt service routine vector, because that's really important to the operation of your system. An operating system is demand driven. An interrupt happens, the operating system responds. And that's how many operations in an operating system are invoked. And so these partitions in memory, usually the low parts of memory from 0 to some number, is where the operating sits, and the high part of memory is typically where the user level processes sit. And so whenever, oftentimes in the literature and in the book, you see a description of an operating system and its relationship in memory to the processes, you'll often see a box representing your memory, and that's what we've been doing. Here's your memory. And then down below, you'll see the operating system and then the processes, process 1, process 2, for example, written in that part of memory above. So that's where that diagram comes from. But nonetheless, every single process is contained in a contiguous section of memory. And so that memory segment, that piece for process 1, that might be here, whatever range of addresses that corresponds to for that block, and then process 2 would sit here, its memory. And so process 1 can only read and write its memory, and process 2 likewise can read and write its memory. Moreover, the operating system can read and write its memory. Okay, and so There are relocation registers, and these relocation registers are really important to be able to move around your processes. They can also be used to protect the user level processes from one another. So process 1 and 2 can't overwrite one another, and also from changing the operating system code. Because if you could inject new code into the operating system as a user level process, well, that's effectively what a virus does. You could take control over what the operating system is doing, and because it has privileged access to all the resources on the system, that would be quite bad on a multi-user system, or even things like a server where you have multiple processes invoking requests from the outside world, triggering them, and the server responding. And so the base register contains the value of the smallest physical address. And so the limit then contains a range of logical addresses, and each logical address has to be less than a limit. So you have this notion of a starting place in memory for a process. So here's your OS, a starting place, and that's your base. And then the limit tells you, okay, how far can your process go when it's trying to read and write memory? And so this idea of the base and limit are used to keep your process, say P1, from accessing memory that belongs to process, for example, P2, if this were your main memory. And so the memory management unit, we said, maps between the logical addresses and the physical addresses, where logical address is a process concept and a physical address is a memory concept for memory location. And so the MMU maps logical addresses dynamically. The processes traffic in logical addresses. And so you can then allow actions such as kernel code to be transient and the kernel to change in size if you do this type of allocation. If the kernel's in here, well, the kernel can grow and shrink and do all sorts of things because it has its own walled off sandbox, if you will, region of memory for it can use for its purposes. And so here's an example, the schematic is in the book, of the hardware support of relocation and limit registers. So you have your CPU running your process code, and it generates a series of logical addresses. So then it says, okay, did that address exceed the limit address for that particular computation? If it did exceed it, meaning that less than limit register value is no, then you issue a trap and the operating system handles that. You get a core dump, segmentation violation. If it is less than or within that limit for the block of memory addresses for that process, then it goes ahead, looks at the relocation register, and maps between its logical address using that relocation to create a physical address that it then uses to access that particular physical address to get that code or data from memory. Okay, and so one of the key developments in how main memory is used was to have multiple partitions that are allocated. And in doing so, the degree of multi-programming is now only limited by the number of partitions. So you have your piece of memory, your main memory. I just kind of draw it in here. And you cut it up into a bunch of partitions. And then each time a process P1, process P2, process P3, etc., wants to run, it's loaded into one of these segments into which your memory has been partitioned. And so you can have variable size partitions for efficiency, and these partitions can be sized to the needs of a specific process. So if P1, P2, P3 need different amounts of memory, well, you're going to allocate them to different memory segments that are sized differently. And so in this nomenclature for dealing with memory segment and partition allocation, there's the partition itself, but then there's this terminology called a hole. Now, a hole, it's in the book, it's a block of available memory. It's memory that is not currently being allocated. It's available for use. And so you can have holes of various size scattered throughout your memory. So suppose if you allocate one small block to process 1, a medium block to process 2, another medium block to process 3, you would have certain regions of memory filled in or populated with your processes, but then you'd have some that do not get filled. They're available for allocation to some process, and that's called a hole. So let me direct your attention to the bottom of the screen. We have a number of allocations from some initial configuration. And so here we have the low part, 0 of memory, and some maximum address, n. And so the operating system is resident in the low part of memory. It does not change from step 1 to the next frames, 2, 3, to 4. And you notice the OS is still there in the low part of memory. Now, of course, in this diagram, its low part is at the top, but usually you see in many texts, the operating system low part is here, 0, and N is up top. And so here we have a block of memory, and we have different sized partitions allocated. Process 5 is here. We have process 8, which is pretty big, and process 2, which is also relatively small. And so here then, process 8 runs, and then it exits. Its burst time is complete, and it leaves a very large hole. So here's a hole right in the middle. So now process 9 comes along, and it's allocated a block of memory, and it uses that particular carved out contiguous region of memory from that available large hole. And so now here's process 9, and it leaves another hole. The hole is a little bit smaller because process 9 took up some of that space from the original really large hole. And then process 10 comes along, it gets allocated a block, and now here's our remaining hole. And so in each case, we allocate memory in a variable way based on the size needs of the particular processes that need to be loaded into memory. And that leaves a hole, and that hole can also be of various sizes, and it grows and shrinks over time. And so when a process arrives, it's allocated memory, and it only considers a hole that's large enough to accommodate it. And this process, when it exits, it frees up its partition, making it available for other new processes that arrive that want to either come from swap or come from the disk drive to start being scheduled, added to the ready queue. It's now available, these holes, to be allocated some other process. And so the operating system maintains two pieces of information: a list of all the allocated partitions and a list of all the holes, your free partitions. And so anytime a new process comes along, it says, okay, what are the process image size needs, right? The image size of that process. Let me now select a hole that's big enough, so greater than or equal to the size needs for each of those processes that need to be brought into memory, be that from disk when it's invoked, or be that from the backing store because it was being swapped back in. And so there are many different ways that you can select a hole. These three major flavors, as it were, for how you select a hole is called first fit, best fit, and worst fit. So with first fit, and they each have their drawbacks and benefits, but with first fit, you allocate your process to the first hole that's big enough. So you just go through that list of holes. Oh, that's big enough. Let me just allocate it. Best fit, you're trying to optimize on how tight that fit is. And so with best fit, you allocate the smallest hole that can accommodate that particular process. And this requires you search the entire list. You try against each hole, and you see how much is left over, and you select the hole such that when you allocate it, that remaining part that's unused, that leftover, is the smallest as possible. And so this best fit produces the smallest leftover hole because you're always making sure the smallest hole is chosen to satisfy the needs, of that process that needs it. And so the worst fit then says allocate the largest hole. Now, there are reasons why you might want to allocate the largest hole, but this one produces the largest leftover hole. And in worst fit, you allocate the largest hole that you have available, and you have to search the whole list to do that. And so first fit and best fit are better than worst fit in terms of speed. Well, first fit is fastest because you just take the first one you come to on that list. You don't have to iterate through the entire list of holes. And best fit is better in terms of the storage utilization. When you pack your process into a hole, that process is occupying as much of the hole as possible instead of leaving leftovers that are unused. And so this idea of leaving leftovers can happen two major ways. One's called external fragmentation, and the other is called internal fragmentation. So let's visualize. So suppose we have here some holes. We have a small hole, and let's say we have a little bit bigger hole. Let's say these two are the same size. So we have a small and we have larger holes. Now suppose you have a process, and that process occupies a small hole's worth of space. So here's my process P1. And so my process then, when you're allocating it, two things can happen. And so let's say this first hole was occupied, that last hole, so that's occupied by some other process, let's say P2. And when P1 comes along, If it's allocated some other hole, okay, well, it goes into this hole, so that's occupied by process P1. And so what the external fragmentation refers to is these holes that are unallocated, and it's a total memory space, this external fragmentation, that is available to satisfy a request. And so this particular hole here, it's available for some process to come along and be allocated to it. Now, of course, if you had more holes than that, you could have 1, 2, 3, and here's P2 occupying that. Here is P1. Let's say P1 is allocated here. Now we have this hole, first hole, and then we have our second hole. Now, of course, the external fragmentation is the combination of all of the holes added together, right? That's the total memory space that can be used to satisfy a request, because if another process, P3, comes along, it can be allocated to the first hole or allocated or loaded allocated to the second hole. So that's external fragmentation. Now, internal fragmentation represents that overlap part, that extra part for the whole once it's assigned to the process. And so let's say we have 3 holes here available, and process P1 comes along and it's allocated to this hole. And let's say that process P1, it only occupied that portion of the hole. Now, that remaining part here, that is unallocated. No one can use it because that entire segment was allocated to process P1. So this whole segment was allocated to P1. And if it only occupied some fraction of that segment that was allocated to it, no other process can come along and be assigned the remainder portion, the remainder. And so this remainder portion, if we were to add that up across all of the segments, that would be our internal fragmentation. And so it's internal to the segment. Internal fragmentation, allocated memory is slightly larger than what is requested. So you assign a segment to a process, and there's some remainder left over. And so that difference is internal to a partition. It's not used by anyone else because P1 has exclusive access. Remember, the relocation and the limit register disallows P1 and any other process from accessing P1 space and P1 from accessing any other processing space. So that being the case, this remainder is completely unusable. It's gone to waste, and that's called internal fragmentation. All right, and so in order to reduce the external fragmentation, something can be done about it. You can do what's called compaction. And with compaction, you're going to have to move some contents of memory around. And so let's say you have process P1 that's in the first memory segment, and then let's say you have a hole, and then you say you have process P2 that's in the next memory segment, and then you have a hole, and let's say you have process P3 that's in that last memory segment. So here's P1, here's P2, and here's P3. So you have a hole here, and you have a hole here. Now, what external fragmentation reduction means is instead of leaving small holes scattered around your main memory, you want to put them all together by moving things around. And the relocation registers makes this very possible. So if I were to shift these around, so what would I do? I would move P2 down this way, and I'd move P1 down that way, and leave a lot of contiguous space at the top, for example. So when I'm done here, I have P3 down here, I have P2 here, I have P1 here, there's P1, P2, P3, and now what used to be those 2 holes, and I'll draw a dotted line to connote that, what used to be hole 1 and hole 2 is now one big contiguous block of memory. And so that reduces the external fragmentation because you're taking all of the processes and you're shifting them around in memory using your relocation registers to free up a large contiguous block of memory. And so with compaction, and that's what that process is, you're shuffling the contents of memory to place all the free memory together in one large block. And compaction is only possible if your relocation happens at execution time, if it's dynamic. And so that's really, really important. If it's dynamic, that means every time you need to execute, you can certainly move it around by picking up its contents, changing the relocation register, and putting it down someplace else. But there's a problem here. If you have I/O happening, what occurs? Well, if process P3 is in the middle of executing an interrupt, let's say to get data from the network card and transfer it to that process, reading inbound information, well, that location where the direct memory access transfer is going to happen from the I/O buffer of the I/O device for the network card to this memory where process P3 resides. If you move process P3, there's going to be a problem. It's no longer going to be there when the DMA interrupt finishes and actually is ready to push that data to that prescribed memory location. And so you have an I/O problem. What typically happens is you latch or pin this job in memory while it is involved in I/O. When you are, say, P3 and you're involved in I/O, it's now off limits for being reshuffled when you need to do compaction. And so you don't do I/O into just operating system buffers. You could do that, and the I/O, the operating system buffer, then transfers it back through the return value. But if you're not doing that, you have to make sure that those processes stay put because the DMA controller has no idea that this process has been relocated. When that transaction is set up for the DMA transfer, it goes from that device to that memory location. And that transaction is established so that when the service routine is acting on your behalf within the OS, that transfer knows, okay, when I get this buffer from the device, I'm going to push that content into that memory location. And so you can also think of this fragmentation. When you look at the backing store has the same problems for fragmentation because these segments information is how you store processes on the backing store. If you're going to have segmented memory and you're going to have all of this allocation and you're going to have holes, you're also going to represent, as we said before, the in-memory representation of a process is what they are stored as in the backing store. And so that means we're also going to have fragmentation issues that can happen on the backing store part of your disk. All right, so let's look at this idea of paging. Paging takes this idea of segmentation and relocation, and it kind of standardizes it to make it a lot easier to store your processes to avoid, to a larger degree, this external fragmentation. And so the physical address space of a process can certainly be non-contiguous. And so while you think that your process P1, is one long set of instructions in a stream of instructions, instruction 1 through instruction n, when you actually store this process, it can be stored in memory as a bunch of non-contiguous blocks. And so all of these blocks together would be the first piece of process P1, the second piece of process P1, the third piece of process P1, and the fourth piece of process P1, and so forth. And so when the physical address space of a process is non-contiguous, you can now allocate physical memory whenever it's available. And so this avoids or significantly avoids altogether external fragmentation because you have much smaller chunks and you can now allocate those small chunks to avoid that fragmentation. And this also avoids the problem of varying sized memory chunks. You can have a small standardized unit of memory and therefore don't have that issue where some processes need a huge block and some need a small block. If you have a large process, you just need a larger number of these small standard sized blocks. And so essentially what happens is you divide your physical memory into fixed size blocks. And these fixed size blocks have a name, they're called frames. So you also, these frames, when you look at their size, the size is always a power of 2 when you talk about chunks. So 2 to the 1, 2 to the 2, 2 to the 3, anywhere from 2 to between 12 bytes, and which is 2 to the 128, that's 256, that's 8, 9, 10, 2 to the 10. And so it's between 5 12 bytes long, the size of one of these chunks, and 16 megabytes. They can be quite large, these frames, these units of physical memory. And so you also then divide your process, this logical address space, into blocks. And the one caveat is really, really important, is that the block size for a process has to be identical to the block size of your memory. And so therefore, one of these logical memory blocks is the same size as the physical memory blocks, and these logical memory blocks have a name. They're called pages. And so here you have your process. Let's say that's process P1, and here you have your main memory. And let's say process P1 is divided up into pages. Here's page 1, page 2, page 3, and page 4. And now your memory is divided up into page frames. And so let me draw similar sized pages. So that's about the same size. And you notice here the memory has a lot more number of page frames than the process has pages. And so these are pages, and these are called frames. And sometimes in the literature, you'll see the name page frame. And so then you take process P1, its first piece might be here, its second piece might be here, its third piece might be here, and its fourth piece might be here. And so now this collection of pages that have been loaded into page frames is that set of standard size blocks of memory in collectively that comprise process P1. And so whenever you divide up your memory, the logical division is called a page, and that has to be the equal size of the physical division, and that's called the frame or page frame. Okay, and so now what the operating system needs to do is keep track of all of the free frames, similarly to how it kept track of all of the free segments. And in order to run a program of size n, right, you talk about the program size as being the number of pages comprising that logical address space for the program, you now need to find n free frames from your memory and load those n many pages into those n many free frames. And so there's a construct called the page table, and this page table's name is to translate from your logical representation of your program to the physical address in memory. And so you're going to translate from which page and which location in a page for a process to which frame, and that location stays the same. And that's why the size of the page is the same size as the frame, because this offset within a page for the instruction is also used as the same offset within a frame for the memory location. And so you set up this page table, and then backing store is also split into pages. Again, the backing store is nothing more than an on-disk representation of what the in-memory representation is for your process. And so you can still have internal fragmentation, but because your pages and your page frames in memory are relatively small, that amount of internal fragmentation is not going to be terribly big, because again, your size of your unit is between 512 bytes and 16 megabytes. You're not dealing with enormous blocks for the page frame size. All right, so let's take a look at the form of this address. And so an address is some number of bits, and this address is a total of m many bits. Now, of course, if you're dealing in bits, if you have some number of bits, that represents 2 to that number many choices. And so our page number and our page offset is how we interpret this address, and they're concatenated together to form a single address. And so if we look at it, the page add number, P, and that's going to be a number, and it's going to be used to index into a page table. Now, this page table is just a table, the data structure, page table, and this page number, P, has some value, and it's going to refer to some entry in the page table. Now, inside of that page table, it's going to contain a frame number, and that page frame number is where you will find which block in memory, which page frame in memory, you're going to find that particular block of your program. And so this page table maps between page numbers and frame numbers. That's from the logical page number to the physical frame number. And so the other part is a page offset D. And that page offset tells you where within the page that particular instruction is. And again, that offset is the same because the frame size and the page size are identical. So if you have an M many bits representing your address, well, we have N of those bits representing the page offset, that number D. So that means D is going to be anywhere from offset 0 through offset 2 to the n power minus 1. So you're going to have a total of 2 to the n many offsets for an n-bit page offset part of your address. And then the remaining m minus n bits is going to be your page number. So how many pages can you have? How many offsets into your page table? Anywhere from page number 0 up through 2 to the m minus n power minus 1. So that's a total of 2 to the m minus n power many page numbers or many offsets into the page table. And so for a given logical address space, you're going to have 2 to the m as the size of the logical address space, but those 2 to the m addresses are going to be a certain offset within a certain page number in your program. And your page size is going to be 2 to the n total, because that page is some number of offsets labeled from 0 to 2 to the n minus 1. All right, so here's an example of the paging hardware. We have our CPU, and it's generating a logical address, and we have the lower bits representing the offset. Well, that's just transported forward because the page size is the same as the frame size. So the offset portion doesn't change. But the page portion is used to index at the piece entry in the page table. It looks up and finds a frame number, and that frame number is going to be used to fill in the frame portion for the physical address. And so the frame number says which frame. It's the first frame, the second frame, the third frame, or the F frame. And that's going to be the physical address, which is just the looked up frame number where that page has been loaded, and the same offset. And that's your physical address. So here's an example. We have on the left here logical memory. So this is your process. And this process has 4 pages: page 0, page 1, page 2, and page 3. So that's your logical representation. And you'll notice here the page size is the same as the frame size, or the page frame size. So here we have a page table, and so the 0th entry in the page table corresponds to the 0th page of process. If we look that up, it's in frame number 1, and we see that page 0 has been loaded in frame number 1, and it completely occupies because they're the same size. Likewise, page 1, okay, we're going to refer to the first offset in that page table, and we see that it's in frame number 4. So we see frame 0, 1, 2, 3, 4. We find its contents is page number 1 from the process, and it completely fills that. We've avoided external fragmentation. Likewise, page 2, look in entry 2 of the table, it's in frame 3. So we go 0, 1, 2, 3, here's page 2. And then lastly, page 3, it's in frame 7. That's 0, 1, 2, 3, 4, 5, 6, 7. Here's page 3 in memory location, or in frame 7. All right. And so here's a more sophisticated example. This is also in the book. And here we have logical memory. And in this particular case, we have the number of bits for our address, or logical address, is 4 bits. Now, of that 4 bits, 2 of them are going to be the offset. And so because 2 to the 2 is equal to 4, that means we have pages that are 4 bytes long. So that's byte 0, 1, 2, 3. That's byte 4, 5, 6, 7. So each page is 4 bytes long. And so we have here, we have page 0, we have page 1, page 2, and page 3. Okay. So now our memory here, we have a 32-byte memory. 32 bytes is the same as 2 to the 5. 2 to the 5 is equal to 32. So that means our memory It's total 32 bytes long. And remember, we said that the page size is 4 bytes, uses 2 bits. And if the page size uses 2 bits, that means our memory at 32, we have 2 to the 3 times these 2 to the 2 size frames. So each frame is 4 bytes. So this is our main memory, and these are our frames, our page frames. So we have 4 byte frames. That counts for these 2 to the 2 for our offset, because the offsets are the same, because the page's size is the same as the frame size. So that means we have 2 to the 3 of these 4 byte pages. 2 to the 3 is 8, so that's page 0, page of frame 0, frame 1, frame 2, frame 3, frame 4, frame 5, frame 6, and frame 7. So we have a total of 8 frames, each 4 bytes. 8 times 4 is 32. All right, so now let's look at our page table. So for page 0, it is located at frame number 5. So this frame number 0, 1, 2, 3, 4, 5. And you'll notice stored is A, B, C, D at each one of those offsets, offset 0, 1, 2, 3, within page 0, because it's located at frame 20, here we see A, B, C, D. Now if we look for frame 1, that's located in page number 1 is located in frame number 6. It's this entry. So if we go 0, 1, 2, 3, 4, 5, 6, there's our page number 1. So page number 1 is located in frame 6. We see the E, F, G, H loaded into frame number 6. All right. If we look at page 2, it is in frame number 1. So I, J, K, L, we see frame 0, frame 1. I, J, K, L, each one of those offsets 0, 1, 2, 3 within page number 2. And then lastly, we have page 3 for our program. It's been loaded in frame number 2, 0, 1, 2. So we have the MNOP. Here's MNOP. Our page number 3 is loaded in frame number 2. Okay. So the important thing to remember is how you translate from the page to the frame, going indirectly through the page table. And it's important to note here is that when we look at the size of memory can easily be more frames than you have represented for a single set of pages for a single process. Okay, so let's look at this idea of free frames. And here we have a free frame list, because if you talk about holes in a list, now that we're dealing with frames, is a list of these unallocated frames. And so in the frame list, free frame list, we have frame number 14, 13, 18, and 20 in that order. And then we have a new process. Now this process could be loaded in the backing store, or it could be coming off disk for the first time as it's invoked. But nonetheless, this process has page 0, 1, 2, and 3. So page 0 is first going to be allocated, and it gets frame 14 that it's assigned to. And then page 1 comes along, it gets the next one. And then page 2 comes along, gets the next one. Page 3 comes along, gets the next one. And so here we have page 0 is in frame 14. So we have frame 14, there's page 0. And then we have page 1, 2, and 3 get frames 13, 18, and 20 respectively. So page 1 is in frame 13, here's 13, and page 1 is there. Page 2 gets frame 18, and so we look at 18, and page 2 is there. And lastly, page 3 for our process is allocated to frame 20, is frame 20, and we see page 3. And so then when we look at the page table, the new status of the page table, we have page 0 is in frame 14, page 1 is in frame 13, page 2 is in frame 18, and lastly, page 3 is in frame 20, as we had just gone over. And so the free frame list now has updated. It has allocated the first 4 frames from the frame list to page 0, 1, 2, and 3. And so the only free frame left from this example is frame 15. And you'll notice here it's unallocated. All right. So let's take a look at the implementation of this page table. It has to be kept in main memory. because it needs to be relatively fast. And it has two governing registers, a table base register, so the process knows where the beginning of the page table is, and a page table length register, so it knows how many entries, the size of the page table, because you're going to be allocating a slot in the page table. And so this requires two memory accesses, one to reference the page table, and then once you get the frame, then to actually access memory itself. So that means you have two memory accesses, one for the page table, one for the actual memory when you're trying to go through the paging allocation. And so we said before that the CPU operates much faster than memory. And if you're waiting for two memory accesses for one loading of a process into its pages into a page frame, that can introduce a memory stall, and that is really expensive. And so a solution to this is to have some fast cache-like memory on the CPU that's used to speed up this association between the page offset and the frame number in memory where that process's page was loaded. And so this is accomplished through something called a Translation Lookaside Buffer, or TLB, which is a type of associated memory that caches the association between a page number and a frame number. And it runs at chip speed. And the more you access something, the more it stays in this cache. And so some TLBs store address space identifiers, and the TLBs are typically very small, and you need to flush TLB every time you switch between processes because these associations of mappings between pages and frame numbers is specific to the process. But these things nonetheless are very small, and a so-called TLB hit means that when you give this TLB a page number, the associated frame number is already in the TLB. A TLB miss is a situation where you give this TLB page number and it does not have a frame number associated with it, so it has to now access the page table in order to retrieve that frame number or allocate the frame number. And so you have, as this TLB acts like a cache, and it has an invalidation policy should you need to, if you exceed all of the mappings that are currently in a TLB. And so as an associative memory, you're implementing a kind of search, and it's parallelized. You have the page table, page number, that's the page entry, and then you have the associated frame number. And so this atlas translation happens from pages to frames. And so if you have your page in the associative register, you get a frame number out. Otherwise, you have to retrieve this frame number from the page table, a so-called TLB miss. And so this schematic is in the book, and it describes all of the components involved in the TLB function. And so here we have our CPU generating a logical address that consists of the page number portion and the offset number. So that offset is propagated forward to the offset portion of the physical address because the pages and the page frames are the same size. And so then you take this page number and you look up in the TLB. If you have a hit, then you just take the associated frame number and you push that associated frame number for that page where it has been loaded into the frame portion of the physical address. If you have a TLB miss, you go to an offset access the page table to that offset for that entry P into the page table, get the frame number, and use that frame number. And then, depending on your invalidation process or policy, you're going to then add a new entry to your TLB that has that page and that newly looked up frame number if you have a TLB miss. So you can either have a TLB hit or TLB miss, and this TLB, when you have all hits, this runs at full speed instead of incurring that memory stall every time you want to map a logical address to a physical address. So it's really expensive to stall every time you're going to do that, because if your CPU through your program counter is going to get the next instruction, invariably it's going to generate these logical addresses quite frequently, and it's a huge slowdown to your performance if you have to do these memory stalls for two memory accesses, one for the table lookup and one for the access, every single time you're going to generate an address. And so this TLB, you can think of it as an associative memory, almost like a hash map, to use a Java-ism, and this thing populates, and you can either get a TLB hit or TLB miss, and when you get hits, you are saving memory stalls by not having to look up information in the TLB each time in the table in the page. You are getting a savings by not having to look up in the page table every single instruction access and incur that memory stall. So memory protection is another feature that is implemented in paging. And so in memory protection, you have a bit that is associated with each frame, and this bit enforces whether or not you can read or read and write access the memory and instructions associated with that particular frame. And so there's also a valid invalid bit, and this indicates whether or not the page is in the process's logical address space. Has it been loaded? Is it a legal page? And so this is implemented as a page table register, and this bit enforces these protections and these mechanisms. And so here we have our logical process, and we have 6 pages, page 0 through page 5, and we also have our page table here. And here we have the frame number entry associated with each page, and then we have an associated valid bit. And so in this particular case, we see that pages 0, 1, 2, 3, 4, and 5, they're loaded. Page 0 is in frame 2. There's page 0. Page 1 is in frame 3. There's page 1. Page 2 is in frame 4. There's page 2. There's page 2. Page 3 is in frame 7. There's page 3. Page 4 is in frame 8. There's page 4. And page 5 is in frame 9. There's page 5. Now, pages 6 and 7, they are marked as invalid, whereas pages 0 through 5, they're valid because they're in memory, loaded in a frame, and therefore in the logical address space of the process. Now, we don't have a page 6 and page 7, but if we were to have a page 6 and page 7, then you'd have values filled in for the frame number, and they would be valid bit set because they actually exist. So if a page is physically there, loaded, and you can access it, it's in the address space, this valid bit would be set to valid. In addition, you can have these protections whether or not you can read only or read write the various pages. All right, so you can use pages beneficially to share code. Oftentimes, there's certain code that is read-only, so-called re-entrant code, where you're not going to write data. And so if you're only going to read it, like the instructions for a program, you might want to share it so that this different processes don't have to load multiple copies of it in memory. You only physically have one frame populated with this code that's shared among different processes. And you can share things quite easily if they're read-only. You only care about that synchronization that we talked about if you're going to write something or update the value. And so suppose you have text editors, compilers, windowing systems. There's certain types of code that they might rerun all the time. Rather than having 5 processes each load their own, just load one and have all the processes use or share that one segment. And so in this case, you can have multiple threads sharing the same part of a process address space. But it's just the idea of mapping that particular frame into the local address space, the logical address space of each process. And so this is also useful for inter-process communication if you're able to share, and that's a big if you're able to share read-write pages. And that's how something like shared memory is implemented. You can also, each process can keep a separate copy of the code and the data. If you're not doing any shared pages, they're all separate. All right. And so with that, that's all I had. We will end there. I'll just show the key milestones again. And as it is Thursday, as usual, have a great weekend. Please make sure you're keeping up with the work and note down these key dates for the rest of the semester. We have 4 weeks remaining after today being Thursday, 4 weeks remaining. So please stay on top of everything. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.